Okay, today I will give a brief introduction about symplectic group. And first, I will give a reason why that I choose this topic. Because in this semester, I take a general algebra class, and in this class, I learn about some special group. So I choose this spatial and fantastic group structure to be my topic. Yes. Um, Next, I will go to give some basic property about quaternion. Quaternion, yes. Um, okay. Okay. We see that quaternion is similar to a complex number. The first coordinate is real number, and the next three coordinate is like complex number. And this this quaternion will have some property. First, we see that I squared equals to j squared equals to k squared and equals to -1, and ij equals to k, jk equals to I, and ki equals to j. And next is similar. Yeah. We can get this result by above two property. Yes. Um. Okay. And next we will going to talk about the linear maps between the quaternion. Okay. First we let K be a skew field, and V and W be vector space over K. Yes. And then we called a map F from V to W is linear over K, or K linear if this map satisfy these two things. Yes. And we call endomorphism or linear transformation of a vector space V over K is K linear from V to itself. Yes, just like uh, in linear algebra. Yes. Um, the endomorphisms of V over K form an algebra over K denote this. Yes, it is a common symbol. Yes. And endomorphism is invertible if and only if they have two side inverse. Yes. Okay. Okay. Oh yes. And and there are there is a important group structure. Is called the general linear group. Denote like this and this. Okay. And okay. Next, we let the set E1 to En is standard basis for Kn, and Kn is vector space over K. Yes. And if we let F is K-linear map, then easily we can check Fej equals to this. Yes. And matrix A called the matrix O of F. Yes, it is a representation of F. Yes. And let X equals to this. It is belongs to the vector space Kn. And we can easily get Fx is equal to this. Yes. And the I component of Fx is equals to this. Okay. And in matrix notation, we can represent this property by this equation. So by above construction, we get there is an algebra isomorphism between endomorphism Kn to K m by n. Yes. And the group general linear group correspond to the group of all invertible matrix over K. Okay. Next, we will give some property about the quaternion conjunction. Like complex number, the conjunction of quaternion is let the sign of ijk change from plus to minus. Yes, just like complex number. And by simple computation, we get for any two quaternion, their conjunction is equal to one conjunction multiplied by the other quaternion conjunction. And the location of two conjunction will change. Yes. And it is important that for any matrix A where it belongs to Hn by m, it is not true that AB conjunction equals to A conjunction B conjunction, but it is true that AB conjunction transpose is equals to B conjunction transpose multiplied by A conjunction transpose. Yes, it is an important property. Next, we will talk about quaternion inner product. And just like the inner product we learned in linear algebra, we define the quaternion inner product by this equation, and it has these two properties. Yes, And next, um, we say that the map F from V cross W to H is linear over H if it is conjugate linear on the left in the first argument, this, and linear on right in the second, like this. Okay. Next, we will talk about how to use a complex number to represent the quaternion number. Okay. By the above uh, discussion, we know that the quaternion number is in the form of A plus IB plus JC plus KD. Yes. And it is obvious that it can be written as this form. And when you let mu equals to A plus IB and let V equals to C minus ID, and we get the form that mu and V belongs to complex number. And it is clearly that we find a basis 1J and Hn is a vector space over C because mu and V is a complex number. Yes. Okay. By above discussion, we can use some simple computation and we get the property above. Yes. Okay. And we can make some observation that if we multiplicate some quaternion by left, and we get that these two equation is hold, and by the scale from linear algebra we get the matrix LQ can be represented by this matrix. Yes. And this is an interesting part of this section, I think. Yes. Okay, next. We will going to talk about the norm of quaternion number and in the term of complex component. And in last section we are going to we have talked about the inner product of quaternion number, and we now that we redefine it by the complex form of quaternion number, and we can write it like this. Yes. And final we get the two component of the inner product is like this. And by this inner product, we can define the norm of quaternion number, and it is like this. And by this equation, we can easily find that the norm of quaternion number is like this. It is the form of the norm of Euclidean space, just like we think. Yes. Okay. Next, we are talking about the H linearity. Okay, let we see property. Now V is a quaternion vector space, and now F is a H linear map from V to V. It's equivalent to the condition that this map is also C linear and satisfy that F yes, it satisfies this equation, and this side is clear, and the other side, and first we suppose that it is satisfied that F is a C linear map and F is commute with Rj, just like this equation. And by C linearity, F is additive and commute with R mu, and for any compute number mu. And for any quaternion number, we can write it in a complex number form. Q equals to mu plus JV. Yes, and we can split this multiplication RQ into two parts. R mu plus RV， 然后不会念合成 RJ yes, and since F is additive and commute with R mu, RV, and RJ by the C linearity, so we can get that for any Q belongs to H, RQ is commute with F, so F is H linear. Yes. Okay. Next, by above property, because Rj is neither H linear nor C linear, it is easy to check, and so it cannot represent by left multiplication by a complex matrix. Yes. So we can observe that RJQ is equals to this, minus V bar plus J mu conjugate. Yes. In matrix notation, we can easily get this form. Okay. Okay. For a long process for talk about some property of quaternion, we finally get a chance to talk about symplectic group. Yes. Now V be a vector space over a skew field K with conjunction, and that B is a map from V cross V to K, be a bilinear or sesquilinear function over K. Such function is called bilinear or sesquilinear form over K, and we call that a K-linear automorphism is say to preserve the form B if it satisfies this equation. It is important. I mark it with red. Okay. Um, and the set of this automorphism is a subgroup of the general linear group we talked about above. Yes. When K is the skew field RC or quaternion number, and B is Euclidean Hermitian or quaternion inner product space on Kn, and the subgroup of GLNK consisting of automorphism of Kn, preserving each of these inner product, is called orthogonal, unitary, or symplectic group. Symplectic group is what we are talking about, and orthogonal is what we learn in undergrad linear algebra in the first year of college. And unitary is also learned in linear algebra class. It is in the metric of component of metric is complex number. Yes. And these three metrics is denoted by ON, mu n, and SPN. And SPN is symplectic group. Okay. And in particular, we are focused on the symplectic group. And the symplectic group is satisfy this form. Is preserve the inner product. And by this equation, we can write this equation. And we can easily get that if F belongs to the symplectic group, then the representation of F is matrix A that satisfy A conjugate and transpose multiplied by A is equals to the identity matrix. Yes. And we can easily check that Hn is equals to this. And it is isomorphic to C2n. So it is easy to imagine that the group GLNH is isomorphic to the subgroup of GL2NC. Yes. And okay, next we give some example. By above, we can construct a algebra isomorphism between endomorphism H and H. And we can check that the spatial linear group in one dimension is correspond to the quaternion that its norm is 1. Yes. So if we use the property of H is isomorphic to R4, then we can get that spatial linear group of y dimension is isomorphic to S3. That S3 is the unique free sphere in R4. Yes. Okay. And the complex symplectic group SPN 2n C is the subgroup of GL2nC, and it's preserving the skew symmetric Billiard form, like this. Yes. And by the sequence of computation, we get that these two things is equivalent. Yes. Okay. Finally, we give some theorem about the symplectic group. This theorem is talking about that the symplectic group SPN is isomorphic to the intersection of unitary group of dimension 2n and intersect by spatial symplectic group of dimension 2n over complex number, and we give a proof. And if f belongs to spatial symplectic group of dimension n, then by this where yes, by the property E2 in the section E6. Yes, this property. Then we get that F is an H linear, and so it is also C linear, and satisfy this equation. And preserve the Hermitian inner product because we define this group above. Yes, in this section. Yes, it will satisfy this property. So so it preserves Hermitian inner product and the standard skew symmetric Billiard form on C2n. So it belongs to mu2n because it satisfies Hermitian inner product. Preserve it, yes, and intersect the spatial linear group of 2n over C, yes, because I say, oh yes, because it is also satisfy the quaternion inner product that is preserved. The other side, we will show that the condition F this is equals to equivalent to F belongs to unitary group of dimension 2n, and we can write this condition, and we get this by about this where is it? Oh, this by this equation E1 of sections E6. and we can easily get the next equation like this, and we can cancel c from both sides, and we get this equation. And because a is belongs to unitary group, so we get that J is equals to A conjugate inverse multiplied by J and multiplied by A. And finally we get this equation. And by the above conclusion, we can get that F belongs to a symplectic group of 2n over C is equivalent to its representation A satisfy that A transpose multiplicate J multiplicate A is equals to J. So we get that F is belongs to symplectic group of 2n over C. Yes. So we prove the both sides and we finish this theorem. Okay. And this is my presentation about this topic, and I wish you will like it. Yes. Thank you.